time for another exam. Calc 2! Woohoo! We get to flex our integration muscles. We're going to do advanced techniques of integration. It's going to be fun. It's going to be a good challenge and a workout. This is the point where it's like, okay, we're going to test our algebra and our trigonometry skills to the max. So I'm really looking forward to it. And of course, as we do with all exams, we should first put our name on it, because if we don't put our name, we're not going to get the credit. All right, let's begin. Number 1. We're asked to find the integral of x times arctangent of x. Now, personally, I already like this problem because I see an arctangent. I'm a big fan. But okay, let's think about it. What is it they're trying to have us do? And one of the things that we have to learn is how to figure out what's the right technique to use. Now, is there any clues? Well, there is a clue, and it's something I already mentioned, arctangent. Now, how does arctangent become a clue for us? Well, what's true about arctangent? It's hard to integrate because, we don't memorize the formula for integrating arctangent, but it's easy to take a derivative of. Now, if you have something like this, hard to integrate, easy to take derivative, that's suggestive. That says integration by parts. Okay, so let's do a reminder. What's integration by parts say? Well, it says the integral of u dv is equal to uv minus the integral of v du. So what's going on? Well, essentially, it's swapping the u part, you take a derivative of, the v part, take an integral of. And so if you say, oh, there's a piece of my integral that's really hard to work with, but has a nice derivative, you say, oh, make that part your u, and then it will become nice. And maybe nice enough. All right, so we kind of have our plan. We've already said arctangent of x, that's the hard part. So we're going to make this part our u. All right, well, what does that mean for our dv? Well, whatever's left over, that's going to be our dv. All right, so there we go. Now we've got to work through and say, okay, what's u? What's du? What's dv? What's v? Okay. Well, we'll start with du. Okay, so, well, let's just put it all down. U is arctangent of x. Du, the derivative of arctangent, 1 over 1 plus x squared dx. dv is the x dx. I like to include the dx there. So what is v? Well, what's the integral of x? Well, it's 1/2 x squared. All right, so we have the integral of x, arctangent of x, dx, our u dv, has to be equal to our uv. So that's 1/2 x squared arctangent of x minus, all right, well, the integral of v du. All right, so there's v du. So 1/2 x squared, 1 over 1 plus x squared dx. Okay, so what have we done? Now, integration by parts doesn't necessarily reduce the number of integrals. We still have one integral, right? We started with one integral, we still have an integral. But ideally, we have a simpler integral. Notice all polynomial pieces. Nice! Now, once we have polynomial pieces, we can sort of channel a little bit of our partial fractions, but usually it's a little bit simpler than that. Say, okay, look, the 1/2, that's a constant. Don't worry about that. That goes outside. So it's like x squared over 1 plus x squared. All right. Well, So we have 1/2 x squared over 1 plus x squared. And, well, if we were thinking partial fractions at this stage, we'd say, well, let's do a long division. But really we can say, well, you know, x squared looks a lot like 1 plus x squared. We're just off by 1. So let's fix that. So we can fix it by plus 1 minus 1. Now, if you're like, I wouldn't have come up with that, that's okay. That's why long division exists. Long division would have given you the same thing. So, what do we have? Well, we really have 1/2. And now, think of the first piece. X squared plus 1 over 1 plus x squared would be 1. And there's a minus 1 over 1 plus x squared. And each of these pieces is nice. It's something we can work with. Oh, yeah. It's what? Well, 1/2. There's an x. And then there's an arctangent of x. And of course, don't forget, you'll need a plus c. But let's put it all together. Okay, so here we go. All together now. We have that this integral of x arctangent x is, we have this piece, the 1/2 x squared arctangent of x. Don't forget the minus. It's easy to forget minus signs. We're not going to forget them. So there's a minus in front of here. We'll distribute that through. So there's a minus 1/2 times x. So that's minus 1/2 x. Minus 1/2 times minus arctangent x makes a plus 1/2 arctangent of x. And of course, because we want all the points, we're not going to forget. This is an indefinite integral, so absolutely plus c. Because otherwise, oh my gosh, we would forget the plus c. That would make us feel terrible. But we don't need to, because we got it. There we go. Nice. And on a side note, you kind of know that there's a handful of techniques. So you kind of know, like, okay, we're going to expect something is going to be integration by parts, so you got to be ready for it. But let me give you a small warning. Just because you know every technique is used, don't just randomly pick things, right? You want to be smart. And so you say, okay, look for clues. What was our clue here? We had a part that was hard to integrate. So what might that look like? Usually that looks like arctangent, or it looks like log. You might have things where you say, oh, I have x sine x, or x e to the x, things like that. And you say, well, what would you want to do there? Well, in that case, you say, I'd like to get rid of the x. You say, well, good news. If you let x be your u, taking derivatives, you'll knock it down. And then, of course, there's always the curious things like e to the x sine x, where you get into a fun, turnaround, twisting thing, and it's a lot of fun, but that's beyond the scope of this problem. For this problem, we're done. On to the next one. Number 2. We're asked to find the integral of sine cubed of x over 2 dx. All right, what's our setting? What's our tool we're supposed to be using here? Well, everything is trig. This is a trig integral. All right, good. So now that we know we're dealing with a trigonometric integral, we say, okay, what do we do? Well, the goal is to say, what's our right technique? Now, here we have sines and cosines. Nothing's in a fraction, so that kind of simplifies things. We say, all right, there's kind of two cases. One case is where all the powers are even, and then you just got to sort of embrace power reduction until that's no longer true. The other case is one of the powers is odd. And you say, brilliant! We love that. Why? Well, here's what we can do. So when we see an odd power, we're going to pull off one term to the end. So this integral of sine cubed of x over 2 dx, we're going to pull off a single sine term. Now, we'll explain why in a second. Okay, so it's been a second. Here's our game plan, so we can understand what's going to happen. the goal here is to say this part right here is we're shooting for this to become du, roughly speaking. Now, it's not exactly that. We'll have to play with it. But roughly speaking, that's our du. How do we achieve that? Well, the punchline is we're going to rewrite this other part, because now it has even powers, in terms of the cosine. Now why? Well, because the derivative of cosine looks like sine. So this would become our du. So this is the goal. Now, how do we do it? Well, we dig deeply into our trig identities, and well, it turns out we don't have to dig very far. It's actually the first one, the one that people actually remember. Do you remember it? Yeah, it's sine squared of theta plus cosine squared of theta equals 1. So that allows us to say, hey, sine squared, you're 1 minus cosine squared. Brilliant! Brilliant! All right. Well, what do? Okay, so updating. We have, this becomes the integral of 1 minus cosine squared of, now here, theta is x over 2. X over 2. And then we have our sine of x over 2. All right, so here we go. We're ready to carry out our substitution now. We have a single sign. Everything else is in terms of cosines. Life is good. All right, so let u equal cosine of x over 2. Then our du, well, the derivative of cosine is negative sine. Okay, got to remember that. It's tricky. Okay, derivative of cosine, negative sine. The inside, okay. Anything else? Yes. We have 1/2 dx. All right, good. Now where did the half come from? Chain rule. Where did the dx come from? Derivative of x. Okay, well, we say, look, we have a sine x over 2 dx. So we say, okay, no worries. We want to make this look like sine of x over 2 dx. So we multiply. Minus 2 du is sine of x over 2 dx. All right. Well, we're making good progress here. We're making great progress, actually. Well, what's going to happen? So, carrying out the substitution, we have 1 minus u squared. Right? Good. And then the sine x over 2 dx will become minus 2 du. All right. Well, so we can also write this as 2u squared minus 2 du, multiplying the minus 2, which, okay, I'm running out of paper. I'll move a little bit this way. That's 2/3 u cubed minus 2u plus c. Don't forget, indefinite integral, you need your plus c. There you really go after that. We don't want to give them any chances here. Are we done? We've integrated, right? Ooh, not yet, because we need to put the u. All right. So, final thing, replacing u. We have 2/3 cosine cubed x over 2 minus 2 cosine x over 2 plus c. And we're done. We're really done. We made it. Woohoo! Nice. We're already 2 problems down, and we still have plenty of time. We're going to be okay. We're going to be great. Number 3. We're asked to find the integral of e to the 2t upstairs over the square root of 1 plus e to the 4t dt. And I think the first reaction to this problem is like, huh, followed by a huh. what are we going to do? Okay, let's talk about what we're not going to do. We're not going to go crazy. And you might say, well, what do you mean by go crazy? Some people start to panic and they start making up crazy algebra rules. Like they might say, oh, the square root of 1 plus e to the 4t, well, that's like the square root of 1 and the square root of e to the 4t, which is e to the 2t. That's panicking because that's not true. And you might say, but I got an answer. Yes, but it's wrong. And wrong answers don't get as many points. Okay, so we're not panicking. We're not doing that. Algebra still applies. Do we have any clues? Any clues? We have a clue. Remember, what are we looking for? We're always looking for clues. I see a clue, and it's right here, the square root. You say, that's a clue. Now, how is this a clue? Well, square roots tie into trig substitution. All right, so in the back of our mind, we're saying, ooh, this is a trig substitution maybe. All right, so again, see a square root, and then we say, okay, could this be a trig substitution? Now, it's not automatically a trig substitution problem, but on a test like this test, it's likely. Okay, so how do we make it? Well, remember, how does trig substitution work? You have the inside, you have like a squared plus u squared, or u squared plus a squared, or a squared minus u squared. You know, we have these various things. So say, oh, we need to make the insides look like squares. Okay, well, let's start that. So we have e to the 2t, we'll worry about that. Now 1, that's easy to do, that's 1 squared. Now what about e to the 4t? So we right now have a goal. How do I write e to the 4t as something squared? So I want to have something squared. Okay? So the big question, what goes in there? All right. So what, when we square it, will give us e to the 4t. And now we use properties of exponents. See, squaring something is like taking it with exponent 2. It's multiplication. So what goes inside is e to the 2t. So e to the 2t squared is e to the 4t. And now we're like, whoa, that looks like that, e to the 2t. Because it is, right? They're both e to the 2t. So we say, okay, let's make an intermediate step. And let's just, for right now, let's call u equals e to the 2t. Then what's du? Well, du would be 2 e to the 2t dt, or we could say 1/2 du is e to the 2t dt. Okay, so updating, this integral will become the integral. The e to the 2t dt, well, that's 1/2. And I can pull the 1/2 out. Du. And then we have the square root of 1 plus u squared. All right, good. Now, this really does look like a trig substitution problem. So they were kind of hiding it a little bit by like, oh, exponentials, but now it's like, progress. We can make progress here. Okay, so what kind of trig substitution is it? Well, we have 3 possibilities. Let's remind ourselves, because, you know, not only we're doing a test, but it's kind of a short review, right? If you see square root a squared minus u squared, then you say, oh, we should say that in this case, u is a sine theta. If we see square root u squared minus a squared, then that should be secant theta, a secant theta. And if we see the square root of a squared plus u squared, then that should be tangent theta times a. So, idea. We're in this category. So we say, great, no worries. We're going to set u equals 1 times tangent theta. Okay, so now we start unraveling. Well, we say du, derivative of tangent, secant squared. All right, what about this denominator? All right, well, we have the square root of 1 plus u squared. That's the square root of 1 plus tangent squared. And we start thinking, trig identities. What did trig identities say? 1 plus tangent squared equals secant squared. So that's the square root of secant squared, which is secant. All right, so updating again. We're zigzagging through our page here. All right, what do we have? Well, we have the 1/2 still out in front, integral. The du becomes secant squared theta, d theta. The square root of 1 plus u squared becomes secant theta. And we say, well, hey, what do you know? That is secant theta. And now we're like, brilliant! We've gone down to a single integral, and it's an integral which we kind of know. At least it's one of the ones that we are expected to remember. So that's what I mean, we kind of know it, right? It's like, it feels familiar. I think I saw it once. No, we definitely saw it. Integral of secant. That's something we should be able to do. That turns out to be natural log of secant theta plus tangent theta. Okay. And of course, don't forget, plus c. All right, are we done? No, we gotta pedal our way back. Okay, well, what can we say about tangent theta? Tangent theta is u. Oh, okay, well, that's nice. So this becomes plus u. What about secant theta? Do we have something for that? Well, we actually do. See how we have secant theta? That's the square root of 1 plus u squared. All right, good. Now, if we didn't have these, what would we have done? Well, what we would have done is we would have drawn a triangle. I'll do it in a different color. Let's see, what's the color? I haven't used this color yet on this page. We would have drawn a triangle where we just say, okay, put theta in the corner, and tangent theta is opposite over adjacent, u1. So the missing side, square root of 1 plus u squared by Pythagorean theorem. And then we say, well, secant, that's the hypotenuse, square root of 1 plus u squared over the adjacent. All right, now are we done? No. Why? Well, because we didn't even start with u's. Where did we start? We started with t's. So we made actually 2 levels of substitution. And that's okay. We can do that. We can make many. All right, so what's u? E to the 2t. So we say, okay, our last thing, this is 1/2 natural log square root 1 plus e to the 2t squared is e to the 4t, u e to the 2t plus c. And done. Trig substitution. You know what's coming. Be ready. Know your substitutions. And how do you know to look for it? Look for square roots. That's the big clue. If you see square roots, you should say, I should at least think maybe trig sub is a good thing to try here. All right. Well, nice. Let's keep going. This brings us to number 4. Express the integrand as the sum of partial fractions and evaluate the integral. Okay, so we have the integral of 1 over x plus 1, x squared plus 1 dx. Now, is there a clue about what kind of technique we need? Well, there is a clue in that they told us. That's a pretty strong clue. So sometimes they'll just come right out and say, here it is. Okay, not always. But is there something else? Even if they hadn't told us partial fractions, when we look at this, we'd say, oh, this seems like partial fractions to us. Well, there is here, because what do we see? we see polynomial. Polynomial upstairs, yes, 1 is a polynomial, very simple one, and polynomial downstairs. So it's what you call rational function. So polynomial on top, polynomial on the bottom, partial fractions. All right, so what does partial fractions say? First off, worry a little bit about long division. And you say, okay, what's the power upstairs versus the power downstairs of the polynomials? Do I need to carry out long division? In this case, no, we're good to go. But, you know, they might test us, and sometimes they might do something like that. But we're good, we're good. Now, the hardest part about partial fractions is making sure we get the setup right. What's the goal? You know, why are we doing partial fractions? The theme is we'd really like to pull the denominator apart. That's the idea. It's like I want to separate things because a lot of stuff trying to do all at once is hard. But if I can break into two smaller problems, I got a real chance. A real chance. So the goal of partial fractions is pulling things apart. So with that in mind, we say, okay, what's going to happen? Well, we have to find the right form. So we have x plus 1, x squared plus 1. And we're pulling it apart. So we say, okay, so we're going to have something over the first piece and something over the second piece, right? So this is our pull apart. Now there's a few subtleties. If you have, like, say this had been a square or something, make sure you know your subtleties. We won't go into all possibilities right now. But we're not quite done yet. We know this will work for the right upstairs choices. Partial fractions, the main work is saying, what are the right choices for us to have made? And so here's the rule. If what you see downstairs is, you know, first degree, in other words, in fact, it's x plus a, you say, well, the upstairs, it's going to look like a number. If the downstairs is irreducible quadratic, which is just a fancy way of saying you can't factor it any further, there's still an x squared, well, then that says the upstairs is not just a number, it's b times x plus c. All right, so here we go. The main part of this problem is figuring out a, b, and c. And once we have that, we're most of the way there. So how do we get there? Well, okay, once you have the right form, next thing, clean out your denominators. And the way I like to do it, I just say, okay, I'm going to multiply everything by the denominator on that left-hand side. X plus 1 times x squared plus 1. When we do that, what do we get? We get 1, because that's all gone, is equal to a times, okay, here the x plus 1's cancel, so we have x squared plus 1 plus bx plus c, and in this term the x squared plus 1's cancel, times x plus 1. Now there's a couple ways to proceed at this point. One way is we can expand and group coefficients. Another way is make good choices. I like making good choices. It's like your parents. You know, when you went away to college to study and they said, make good choices. Well, now it's our chance to say yes, we're making good choices. Now, what's a good choice? Well, a good choice is something, an option for x, where a lot of things cancel out. So we can get some terms to go away. So for instance, we see an x plus 1 here. So we say, okay, let's plug in x equals negative 1. When we do that, we'll have that 1 is equal to a times minus 1 squared plus 1, which is 2a, plus b times minus 1 plus c times 0. Well, times 0 is hard to recover from. So I say, brilliant. So this tells us that a is a half. Now, is there another good choice? Something which knocks terms out. Well, you might say, but actually, notice how you have a b times x? 0. 0, okay. Let's plug in 0. Let's see what happens. We get that 1 is equal to a times 1. So that's a, but wait, a is a half. All right, we'll write a, but we're going to remember that a is a half in a second. And then b times 0 is 0 plus c, so that's c, and then times 1, 0 plus 1, a plus c. Well, that's a half plus c, so we say, oh, c is a half. Great! We're 2/3 the way done. Now you might say at this point, you've run out of good choices, but that's okay. We only have one number left to determine, so let's just make a choice. How about 1, right? 1 is a great choice, because 1 is pretty easy to evaluate with polynomials. You always want to say, look, be kind to yourselves. We love ourselves, and because we love ourselves, we want to give ourselves a good chance to succeed. So 1 is equal to a times 1 plus 1, that's 2a, plus b plus c, and then times 1 plus 1, which is 2. Now, we already know that 2a equals 1, so we can say, oh, well, what does that tell us? Well, that tells us that b plus c times 2 has to equal 0, because these two terms cancel, right? 1 equals 2a, a equals a half. So, well, b plus c times 2 equals 0, which means b plus c equals 0, which tells us that, hey, b has to be minus c, which means it's minus a half. All right, lots of halves, no worries. No worries at all. So, what does this help us do? It tells us the following. We have that our original problem, let's go back. You might, yeah, at some point we have to do an integral, right? So this part here, partial fractions, this is all algebra. It's not calculus, it's algebra. And doesn't anybody love a good dose of algebra? Yeah, I think so. All right, so 1 over x plus 1, x squared plus 1, dx. Well, now we apply what we've learned here, say, well, this is integral, and we replace our choices for a, b, and c. So this is 1/2 over x plus 1 plus minus a half x plus a half over x squared plus 1. All right. Now, we're going to pull things apart even more, in particular the second term. So we're going to think of we have a half, and we'll do it as 3 pieces, x plus 1 dx. Then we'll have minus a half integral of x over x squared plus 1 dx, and then plus a half integral of 1 over x squared plus 1 dx. All right, now the good news is none of these we can do partial fractions with. So all of these are things like we can integrate. We just have to figure out how. And actually a couple of them are fairly automatic. The 1 over x squared plus 1, classic, that's arctangent. No surprise, right? Who doesn't love a good arctangent on these exams? So this will be arctangent. All right, how about 1 over x plus 1? Now this is one that we should hopefully get to the point where we're comfortable doing in our mind. If you're not comfortable, you could say, well, if you let u equal x plus 1, then du equals dx. This would be the integral of 1 over u du, which is natural log of u. So you say, oh, so this is natural log of x plus 1. All right. So ideally, you'll realize, hey, that plus 1 doesn't really do anything. And so it's like, oh, it's natural log of x plus 1. Great. How about this one? Well, we have to be careful here. It's not arctangent because of the x. But we say, think about it as something downstairs, something upstairs. And you can, whenever you see that, you say, well, what would happen if I took the derivative of the downstairs? It looks a lot like the derivative of the upstairs, right? And what is the derivative of x squared plus 1? 2x. So let's make it a 2x. So we'll make it a 2x by putting a 2 here. And you're like, you can't just put a 2 there. Right, I just can't put a 2 there, but I can if I put a half there. Right? 2 times a half, good to go. And now we're like, okay, we have function in the bottom, derivative of the function in the top, and it's similar to what we just did. We have u du. And we say, oh, it's again a natural log. In this case, it's a natural log of x squared plus 1. So, all together, we have 1/2 natural log of x plus 1, 1/4 natural log x squared plus 1, and a 1/2 arctangent of x. Now I know that arctangent of x feels sad because it didn't get to have a log attached to it. Anything else? Plus c. Don't forget that. Don't forget that. I know I keep saying that, but that's because I don't want to forget it. I don't want you to forget it. But there we go. We got through our partial fractions. Nice. And we actually are over halfway done. It's all downhill from here, right? Number 5. The region defined by 0 less than or equal to y less than or equal to tangent x secant squared x, and 0 less than or equal to x less than or equal to pi over 3. See the figure? So we're going from 0 to pi over 3 and from 0 to the curve. Is revolved around the x-axis. Okay, so we're spinning. And so we spin. So I'm going to add a little arrow to remind ourselves where we're spinning. Find the volume of the generated solid. You should simplify your final answer after evaluating the trigonometric functions. Oh dear. They told us something here. We have to simplify. Okay, so it's not just enough to get an answer. We gotta keep going until we have something which is simple. But I'm optimistic. We should always be optimistic, right? We're optimists here. So, where to begin? Well, this is testing an application. And so we say, okay, it's a volume. So I always say, okay, what's happening with volumes? I'm going to integrate in the x direction because I have a function of x. So integrating the x direction, I think of my slice. Looks like this. I spin, and I say, ooh, that looks a lot like a very thin disk. So it's like, okay, so this is our disk method. Whoops, there we go. Now, how does the disk method work? Well, the volume is equal to the integral start to finish. So we're adding up. We take the area, which is pi, the radius squared, and then there's the thickness. So really you can think of this as area times thickness. That's the volume of a little piece, and add it up. So for us, we say, okay, we know where we're going, 0 to pi over 3. We have the radius is from the axis up to this strange function. And now we say, okay, so it's the square root of tangent x, and then secant squared x squared. And then the thickness is just a little tiny bit of x. We call that dx. All right, so we've done the setup. Whew. Okay, where are we going? Well, the square root initially looks scary, but the square, aha, that's going to be good. So we can pull out the pi. We have 0 to pi over 3. And we'll have tangent of x secant to the 4th x dx. So now we have an integral involving tangents and secants. Now there's a couple of things that happen. Ultimately, in all cases, well, I should say there's 3. One is that we can pull off a secant squared and write everything else in terms of tangent. One is you can pull off a secant tangent and write everything else in terms of secant. And then there's the okay, the case is when we have secants to odd powers, ultimately. That we don't want. All right, so can we pull off a secant squared and write everything else in terms of tangent? Yes, we can. Can we pull off a secant tangent and write everything else in terms of secant? Yeah, we can. See, in fact, it's really well set up for that. See how we have a secant tangent? And then what's left will be a secant cubed. So you say, brilliant. All right, so this will be pi integral 0 to pi over 3. And we're going to have our secant cubed x times our secant x tangent x dx. And by pulling that secant x tangent x to the back, what have we done? Well, what we've done is we said, okay, we've set ourselves up for a good substitution. The derivative of secant is secant tangent. So we're like, let u equal secant. Then the derivative of secant is secant tangent. So we have a du. So now, after this substitution, things get a lot nicer. So we have what? Well, we still have the pi. Nothing happens with that with substitution. Integral secant becomes u. Secant cubed becomes u cubed. Secant x tangent x du. All right, well, progress. Okay, the bounds, don't forget the bounds. So we have to think. This bound here is an x bound. It's x equals 0. X equals pi over 3. We want u bounds. So we say, okay, what is secant of 0? What is that? Well, it's the same as 1 over cosine 0. If that helps. Cosine of 0 is 1. So 1. Okay, 1. All right, what about pi thirds? Secant of pi thirds. Well, that's 1 over cosine of pi thirds. Do we know that? Well, okay, think about the unit circle. And, we often find ourselves thinking about the unit circle, right? So what is pi thirds? Pi thirds is 60 degrees, so it's roughly something here. And the cosine is the x-coordinate. So eyeballing, what should it be? Well, it's not going to be very many things, right? Because there's one of those basic angles we know. So it's 1, root 3 over 2, root 2 over 2, 1 over 2, 0. It's going to be one of those. Which one is it? It's 1 over 2. It's a half. So, since it's 1 over half, we get 2. All right. Well, goodness. That looks like a very nice integral. Cool. And you might notice, after evaluating the trigonometric functions, that's what we just did. After this point, there's no more trigonometric functions for us to evaluate. Okay, well, we're almost done. So we have pi, and then the integral of u cubed is u to the 4th over 4. Evaluate 1 to 2. We don't have to substitute back because it's a definite integral. When it's a definite integral, just keep going forward. And as long as you update the bounds, you never have to go backwards. So, all right, that would be pi over 4. 2 to the 4th, also known as 16. 1 to the 4th, 1. 16 minus 1 is 15. So 15 pi over 4, and we're good. Life is good. What a lovely answer. What a lovely answer. Now, on a side note, if we'd gone a negative number, what would that tell us? We messed up somewhere. And so check your work. And probably the bounds might be one of the trickiest things about this. So, don't rush. Take your time. You'll be fine. You'll be good. Number 6. we're asked to estimate the value of the following integral. Now, even the first word, the word estimate, gives away what we're talking about. Anything dealing with estimation, that's numerical approximation. So it's numerical integration. All right, so what's our integral? The integral from 0 to 1 of 2 sine pi t dt. Using the methods listed below, and evaluate any trig functions and give each answer as an integer or a single simplified fraction. Okay, so this says we have to simplify. Oh, well, no, that's not bad. We don't mind, right? Who doesn't like a little bit of simplifying in the morning? Or the late evening, as the case may be. So, part A. We're going to use a trapezoidal rule with 3 equal width intervals. So we need to remember a couple things. Well, first off, let's figure out what's happening. We're starting at 0 and going to 1. So if I want to chop this into 3 equal widths, well, the total length is 1. So we're going to have lengths of 1/3. So that our points will be at 1/3 and 2/3. All right, now the 1/3 here is important because what's the idea of numerical integration is we're splitting things up and we're approximating this shape, in this case by a trapezoid. So you need to know the width and you need to know the other pieces that make up the trapezoid. So this will come into our answer, this 1/3. And the other thing to remember of trapezoid, well, there's a few things. There's a factor of a half in the front, and then there's this pattern, namely going 1, 2, 2, 2, 2, 2, 1. So a half is the right scaling factor. What I mean by this is saying we're going to weight the points in different ways. So we're going to weight the endpoints as 1, weight 1, and weight the centers as weight 2. So we're giving more weight to the centers and to the ends. And then because of the way it works, we need to add a factor of a half. So it says, okay, everything gets weighted appropriately. All right, so with all of this in mind, we say, okay, we're going to take our factor of a half and our factor of a third. Okay, so we have 1/3 the width, 1/2, which is this correction factor. We're going to have 1 times the first endpoint, f of 0, 2 times the next point, 1/3, 2 times the next point, 2/3, and 1 times the last point. Okay, so there's our setup. All right, now what do we need to do? Well, we plug these in. Now, we said f. When we say f, this is our f. All right, so what do we have? Well, we have 1/6, and we say, okay, plug in f of 0. So maybe we can fit it in here. F of 0, that's 2 sine of 0. Sine of 0, 0. Okay. F of 1/3, that's 2 sine of pi thirds. Well, all right, unit circle. Pi thirds, 60 degrees, roughly up here. The sine is the height, that's the y value, and that is √3/2. I'm timesing by 2. So √3/2 times 2 makes √3. F of 2/3, well, that's 2 sine of 2 pi thirds, and that's over here. It's the same height. So again, it's √3. And f of 1, which is 2 sine of pi, is 0. All right, so what do we have? We have 1/6, 1 times 0, plus 2 times √3, plus 2 times √3, plus 1 times 0. Well, okay, we don't need to worry about the times 0 stuff. That's going to go away. So we have 1/6 times 4 root 3. Well, we can cancel off a 2, and we're left with 2 root 3 over 3. All right, there we go. Good. So now we have our first estimate, part A. On to our next estimate. Simpson's rule. Simpson's rule. Now, Simpson's rule says, instead of, the trapezoid rule says straight line at the top. Simpson's rule says, well, make it look like a parabola on the top. Now, what ends up happening, we're going to split our interval, and now instead of 3, we're going to have 4. So each one of these widths is 1/4. So we can figure out that these are at 1/4, 1/2, and 3/4, our intermediate points. And when it comes to Simpson's rule, what do we follow? Well, we're going to have now a 1/3, and it's going to follow a 1, 4, 2, 4, 2, 4, 1 type pattern. All right, this one is kind of a weird one, but it more or less is saying you should think of it as we look at over 3 consecutive pieces, and 3 points here, and it's really 1, 4, 1, and then we do the same thing here, 1, 4, 1. So this one gets counted twice. So that's why it's a 1, 4, 2, 4, 1. All right. Now, like before, we have to pay attention to this factor here, which corrects for the weighting. So it says everything will ultimately get weighted same amount. And we have our width. Don't forget that. So we have, putting this together, 1/4 times 1/3. And now we're going to take 1 times f of 0 plus 4 times f of 1/4 plus 2 f of 1/2 plus 4 f of 3/4 plus 1 f of 1. All right. Now we say, okay, we are going to do the same thing that we did up here. We're going to plug stuff in and see what happens. All right. So we have f of 0. Well, that hasn't changed. Still 0. It was 0 before. 0 now. We have our f of 1/4. Well, what's that? That's 2 sine of pi fourths. That's our 45-degree angle. Now that is root 2 over 2. And times the 2, that gives us a root 2. F of 1/2, well, that's 2 sine of pi halves. And sine of pi halves is 1, so we get 2. F of 3/4 is 2 sine of 3 pi fourths. Well, that's 45 degree on this side. Again, the height is root 2 over 2, so we end up with root 2. And f of 1 is still 0, hasn't changed. All right, so we have, putting it together, our 1/12 in front. We know that f of 0 and f of 1 gone, because they're 0, right? So that leaves us with 4 times f of 1/4 is root 2, plus 2 times our f of 1/2, which is 2, plus 4 times our f of 3/4, which is root 2. Okay, so that's 1/12. We have, we have 4 root 2 plus 4 root 2 makes 8 root 2, and then 2 times 2 makes 4. We can pull out a factor of 4, right? That's common. So pull out a factor of 4, dividing this, 4 over 12 makes 1/3, 2 root 2 plus 1. And there we go. That's our approximation. Now, which one's the right one? No, that's not the way you think about approximation. Approximations are approximations. They're exactly that. So both are approximating what the integral should be, and it's not to say one is closer or further. It just depends. But there we go. There we go. Whew. Now, I will say numerical approximation can often be one of the most challenging because you have to remember the patterns. You have to remember to scale so everything gets weighted roughly equally. That's what the scaling factor is. Don't forget the widths. That's an easy thing to forget. But otherwise, it's just a matter of plugging away. And by the way, you might notice, this feels like something built for a computer. Yes, it is. Computers love doing it. But for now, we're the computers. All right, one more problem. Number 7, our final problem. Woohoo! We made it to the end. Well, no, that's not our mindset. Our mindset is finish strong. Okay, so what do we have? Find the value of the following improper integral. They gave it away. They even told us what we have. Improper integral. What makes an integral improper? Improper integrals means infinity is involved. So that's what we're after. Okay, so find the value or show that it diverges. So we say, okay, where could infinity show up? 2 places. It could show up in the bounds. Well, no, 1 and 2 aren't infinity. Or it could show up by there being an asymptote. Notice we have x minus 1 downstairs, and x equals 1 is one of our bounds. So that says at one end we're blowing up. So we need to identify our problem spot. And for us, our problem spot is the 1. Okay, so how do we do this? Well, we say no worries. What we'll do is we approach the 1 with caution. So we say, all right, we're going to say that the integral from 1 to 2 of 2 over x minus 1 to the 2/3. And normally, by the way, we would just throw this in and not even think about it. But because it's a test, we know that they're going to be very particular about how we do this. So when we see improper integrals, they really want to make sure we do it with limits. Oftentimes we skip that in practice, but on a test, we want to make sure we know what we're doing. So we're going to have a limit here. So we say, okay, our problem is with the 1. So we're going to take a limit as we approach 1. And since it's the lower bound, I'll put that as an A. And in fact, we can even say, how are we approaching 1? Well, we want to go from a little bit above 1 and keep getting closer to 1. So we're approaching from above. So integral A up to 2. And let's rewrite this integral in a calculus-friendly way. How to make it more calculus-friendly? Well, instead of having it to the 2/3 downstairs, write it as to the minus 2/3, because that falls in line with our rules. All right, so we're going to copy our limit down. A approaches 1 from above. Now this integral we can do. The minus 1 on the inside basically does nothing. It just comes along for the ride. If you're uncomfortable with it, do a substitution. At this point, we should want you to be comfortable with it. So we have the 2. We're going to have in x minus 1, we add 1 to negative 2/3. That makes it a positive 1/3, right? Negative 2/3 plus 1 is 1/3. Divide by 1/3. Well, that's the same as multiply by 3. And here we're going to evaluate A to 2. All right. So this becomes the limit as A approaches 1 from above of 6. Now, 2 minus 1 is 1. 1 to the 1/3 is 1. So 6. Subtract 6. And then we have A minus 1 to the 1/3. And we say, all right, well, we're taking a limit. What's the first thing you do? You plug it in. If you can plug it in and you get a nice answer, you're done. a minus 1 is 0. 0 to the positive exponent, 1/3. We're good. That's nice. So this gives us 6, and we're done. Great. Now, you might say, okay, what are they going to test us on? Well, they're going to be very particular, perhaps. So I want to point out some things that we had. We definitely had the limit, right? But not only did we have a limit, we also had the direction we were coming from. So pay attention to both those things. And of course, part of it is saying, do you recognize where it was improper? So make sure you have that. And sometimes it can be improper in more than one way. So be careful. But otherwise, usually improper integrals aren't too bad. They don't seem that improper at all. So there we go. 7 problems. We finished in under 75 minutes. We have time to go back and enjoy and say, look at all these wonderful things we found, and perhaps try to catch some mistakes, because our goal is to get as many points as we can. Show how awesome we are, how wonderful we are, because we are wonderful. We are awesome. Thanks for coming. Good luck.